well, right now I have identical discs or wheels, and I'd like to talk today about, well, how this is going to roll. Because so far, when we were thinking about what happens on a ramp, it is that objects always slided, never rolled. Now, most of the, I mean, if we make things which we want to move, we usually put them on wheels. And well, so if they are identical, well, they were, I think that they were identical. Let me check it. Actually, they were not identical. And I figured out that they were not identical because they didn't roll simultaneously. Yeah, because, I mean, inside, I have, well, steel balls. And depending on this, how I distribute these steel balls, it affects inertial property of this object. So over here, I put the balls close to the axle. So this will be close to the axle. And here, the balls are further away from the axle. So if they roll, one accelerates faster than the other. And why don't you have a brief conversation and figure out why there is a difference in acceleration, and let's talk about how actually this, where's the difference in the force. So now have a conversation, talk to each other for a moment. Is there a group who already came to a conclusion? All right. How about you then? So why do you think which one moves faster and why?
I think the disc with the ball bearings towards the edge moves faster because the centrifugal force is greater.
Okay, because centrifugal force is greater. Let's look for some other explanations, some other ideas, and then we will discuss which one makes more sense. I mean, which one we accept. Anybody else? How about you? What did you come to? I mean, what was your conclusion? Why? Well, because I saw that you had a vigorous discussion.
Oh, we were just talking about how scaling is not
Uh-huh.
But we were just really
Because when the ball, when we had, correct, yes, I know. So because of angular conservation of angular momentum. So when Taylor was spinning on the platform and he brought the weights closer to his axis of rotation, then he spun faster as well. You wanted to have an idea? You want to say? Somebody here raise a hand.
I'll try, I guess. Maybe it's easier for the inside, like the same force is being applied on a smaller radius, possibly because the balls are closer to the center, so it's being applied at a smaller radius. And maybe
About what forces?
The forces of the balls, like gravity, and I don't know. It's just a guess.
Some other suggestions. How about you?
So you're recognizing that the angular momentum between the two masses should be the same because they have the same mass. So the fact that one of them has been faster because the rotation of the mass being altered.
Oh, so you made an assumption that as the ball, as the discs roll, they have the same angular momentum because they have the same mass, right? Actually, so far, no justification was convincing. I wonder, yeah, because those of you who said that, you had an idea, but I bet that you were not 100% convinced, and that definitely the others were not convinced at all, because the others were coming to completely different suggestions. How about if we think about the forces? Since the objects have the same mass, is the net force exerted on each object has the same value? Are they the same? Net force. Are they? Yeah, because the object is, in those cases, objects are on an inclined surface. Let's identify the forces and find out if indeed, and compare each force for both situations and figure out if they are the same. So let's start with which force would you like to start identify first? Gravitational force, correct. There is a gravitational force exerted by Earth, and where is the center of the force? The center of gravity, which overlaps with the center of mass. Okay, so, and for symmetrical object, it is at the center of that object. So here we have gravitational force. All right, what else? Normal force. Oh, by the way, before we go there, are the gravitational forces identical for both objects? Why? Because they have the same mass, correct. How about normal force now? Where's the normal force? Where's the center of the normal force? At the base, where the wheel touches the ramp. All right. Well, with normal force, we have a problem to determine if they are identical because normal force adjusts itself. Is it clear that the normal force that the normal forces are equal in both cases, or maybe they are not? Who believes that the normal forces are identical in both cases? Who believes that they are different? Those of you who believe that they are identical, you are right, because only these two forces have component in the direction perpendicular to the plane of the ramp, and this component of acceleration is 0, which means that the component of weight perpendicular to the ramp must be opposite to the normal force, and because weights were identical, so this component of weight, these components of weight are identical, so the normal forces are identical as well. Okay, what was well, let's continue with the forces. What else is exerted? What else? Can you identify another force exerted on that wheel? Static frictional force. Where is the center of the friction? Where the wheel touches the ramp. Now, are the static frictional forces in both cases the same? Do they have the same value? So who believes yes? Who believes no? Why do you think that they are no? Yeah, you are the only person who said who disagreed, and on top of it, he is right. Yeah, so he gave me a right justification why the frictional forces are not equal. No, I released them at the same time. Yeah, one was faster than the other, which means that if accelerations are different, it means that the net forces are different. On each object, we had different net force, right? And yeah, because in principle, I should ask you identify more forces. And you should come to the conclusion that that's it. There are only those three forces exerted on the object. Now, the object both objects accelerate in this direction, which means that the component of weight in a direction parallel to the ramp is not balanced by that frictional force. The components of the forces, of all three forces, parallel to the ramp, do not add up to 0. They have to add up to such a value that the object accelerates. Now, what do I mean that object accelerates? If I add those three forces, I will get the net force exerted on the object, and that force is supposed to be proportional to what acceleration of the object? Acceleration of the center of mass, correct? And acceleration of the center of mass were not equal, which means that that one of the forces has to be equal. We see that these two are equal. That frictional force adjusts itself to different value. Do you see that? All right. Why don't we actually now thoroughly analyze that motion, including to finding what is the value of that frictional force. So I'll let's find out acceleration. First, let's find acceleration of each of the ball. And how about if we even think now that for simplicity that we have a solid disk? So it's not exactly problem which we just discussed, but think about the solid disk and how to find out acceleration of that disk. And if I mean acceleration, precisely I refer to what do you mean transversal? What do we mean by acceleration of the center of mass? Correct. So we'll find out how fast this object rolls. Well, we have already free body diagram, and question is acceleration at this particular configuration. So which law would you suggest to use? Actually, we could use any law. Some of them will be easier, some of them will be more complicated. Now, the one which refers to acceleration would be what? Newton's second law. Yeah, because if we use work energy theorem, we will have to calculate derivatives over there. So from speed, we can find acceleration. All right, so let's consider Newton's second law. Well, I can write that mass of the object times acceleration of the center of mass. And now, for simplicity, actually, how about if I concentrate only on the x component, or and so whenever I write a symbol, I will write magnitude of the symbol and relate it properly to the component, because we recognize that acceleration of the center of mass is parallel to the ramp, which means that well, I have a trivial relationship between normal force and weight, because since this component of acceleration is 0, so I can write down then, let's say that this angle over here is theta. So over here I will have angle theta as well, and I can write down that mass times acceleration due to gravity, it's a component of the weight in this direction, must be equal to the normal force. So I can figure out what is the value of the normal force very quickly. However, for this frictional force, it's not that trivial, because the object accelerates. All right, so mass times acceleration of the center of mass is supposed to be equal to the component of the net force. So we have component of the weight, mass times acceleration due to gravity times, consistently with the figure I will have over here, sine of theta minus component of the frictional force. And using Newton's second law, I can create a lot of equations relating interactions with motion. Right now, I related acceleration of the center of mass with the net force exerted on the object. How about if I can also relate it using torques? So I can write, for example, that moment, if I consider, and let's now try to find out convenient points about which we will analyze torques and moments of inertia. Is this point a convenient one? No. How about this one? This one is convenient, because if you consider this point where the wheel touches the ramp, this is an instantaneous axis over here, and the motion becomes purely rotational motion, and on top of it, torque due to frictional force and due to the normal force is how much? 0, right? Because the lever arms are going to be 0. So from that I can find out that this component of the gravitational torque results in the net torque. So I can write down on this side, say 0 plus 0 plus, and this component of the torque, so it will be, I can take this component of weight, right? So torque will be radius of that wheel multiplied by weight times sine of angle theta. This is the torque, and it is supposed to be now proportional to angular acceleration, right? So I can write that this is moment of inertia times angular acceleration. Now I have to write use moment of inertia. Moment, if you look at the tables, moment of inertia of a disk about the axis passing through the center of the disk is going to be 1/2 mass times square of radius. So how can I find now moment of inertia about this point? I will have to use parallel axis theorem. So it's moment of inertia about the axis passing through the center of mass plus mass of the object multiplied by square of the distance between the axes. And the axes are also separated by distance r. Now, acceleration and angular acceleration, I mean, practically it's almost the same if it is rolling. We know what will be the proportionality coefficient, because it is that whenever we have linear and angular, we have to multiply angular velocity by radius and angular acceleration by radius in order radius of the orbit in order to get the speed. So angular acceleration, I can write down somewhere. Well, how about here? That acceleration of the center of mass is equal to angular acceleration multiplied by the radius. Now, how about if I can take another convenient point like this one and also relate torques with angular acceleration? How would I relate these two? So again, I will write that angular acceleration is equal. Now, gravitational torque about this point is going to be 0. So this one is 0. Now, normal torque, 0, right? Because again, the lever arm is 0. So normal torque is 0. How about frictional torque? Is it 0? No. It's also in, right? And lever arm is equal to the radius of the that wheel, and the force is the frictional force. Now that, what do I have to put for moment of inertia this time? Just 1/2, correct, 1/2 mr squared. And the reason is that now I'm considering everything about the center of mass. Now here I have to make a certain digression about it. You can, because in principle, if I attach a coordinate system with a center of mass, let's say that the reference frame of the room is the inertial reference frame, that this reference frame accelerates. So if it accelerates, I mean, I have a certain problem with Newton's second law. Why? Because the reference frame is not inertial. So in principle, Newton's second law should not work there. There is, and indeed, if I, for example, picked this point, I could not use Newton's second law in such a version. I could, however, if I do it with the center of mass, I can do it. Because if you consider torque of inertial forces about the center of mass in that non-inertial reference frame, it's 0. So it's kind of lucky. I mean, we have a good luck over here that if we consider reference frame associated with the center of mass, even if it accelerates, in principle, we should include inertial forces, but by coincidence, inertial torque due to inertial forces is going to be 0. All right. Actually, right now we have probably too many equations. What was our question? I forgot, because I mean, when I analyze, I just see what is related to what, and then when I relate everything with everything, I think, what is my question? Obviously, at the beginning, I had the question, so when I started to analyze, I brought up appropriate relationship. I didn't bring work energy theorem over here. So our question was acceleration of the center of mass. Now let's see how many unknowns do we have. I'm assuming that we know what is the mass of the wheel. This is the only quantity which we know about the wheel. We can easily measure the mass. So if we know the mass, what is going to be acceleration, and we will actually find out that even we don't need that. All right. So Which one will be most convenient? Because really right now it's just algebra. We have to solve algebraically. All right, how about if we take these two equations? Right, if I have I have this expression and this expression over here. So I can substitute over there. So I will have mass times acceleration of the center of mass is equal. And now instead of this expression, I will put this expression divided by r. So this 1/2 mr squared plus mr and divided by r. And instead of alpha, I will put acceleration of the center of mass. Acceleration of the center of mass divided by radius. Did I do it right? No, it doesn't make. But this is still not good. Minus this force. Okay, so static frictional force is there 4, and r squared cancels here. So we will have 3/2 there. And we'll have m acceleration of the center. No, I mean, we need somehow to get rid of this frictional force as well. Yeah, because right now I have two unknowns. From that one. Yeah, over here I have that this is going to be equal to 1/2 mr, and I cancel with this r, and the acceleration of the center, angular acceleration is divided by. But I'm doing something wrong, because I mean it looks like I can eliminate acceleration of the center. Let me check if I got the right equations. This is good. All of them are correct. How about if I first find acceleration of the center of mass, angular acceleration? And from which equation did I do that? mg sine theta alpha. From this one it's easy. Yeah, because over here the only unknown is angular acceleration. All right, so angular acceleration is going to be equal radius of the disk times its weight multiplied by sine of the incline divided by 1/2 mass times square of the radius, and actually it's 3/2. Right, because 1/2 mr squared plus mr squared, so this 3/2. Which means that if I simplify that, I will get 2/3 m and m cancels, g sine theta divided by radius. Okay, so this will be angular acceleration. If we know angular acceleration, now I can find out acceleration. because I have to multiply this expression by radius. And so here I have acceleration. Now, if this was not a disk, but if the object had a different different moment of inertia, what would be different? Because when you saw that when we had rolling objects, they rolled differently. So if I had rather than a disk, I had something else, where would be the difference? I will have to put a different value for moment of inertia. So that coefficient of 2/3 will be, I will get a different coefficient. Okay, so now how about if we find out what is the value of the static frictional force? So now I can plug it in over here. So static frictional force I have to multiply acceleration by mass. So I multiply mass by 2/3 of g sine theta. And move it to the right, so I will put minus in front of that, plus mg sine theta, which means that it is going to be 1/3 mg sine theta. Let me see if it is the right. Now, if object had different moment of inertia, well, then this coefficient would be different. Even this coefficient would be different, static friction will adjust itself to a different value. All right, I know that some of you, because really the algebra becomes a little bit complicated, so just trust me that I performed algebraic steps correctly. I verified that the formulas are the same as the one which I got yesterday. So think about algebra later. I want you now to think about physics. So let's now review again. What did I do? How did I find angular acceleration, and frictional force? Really, the original question was to find the acceleration. So here is the answer. These two were side products of that analysis. But it is also interesting to recognize what is the frictional force exerted by the ramp, and what is the angular acceleration. And this is not, if you think about the solution, it is not a unique solution. Really, I found acceleration, this angular acceleration, using an expression for, this expression, this version of Newton's second law. So really, I was thinking about using Newton's second law about the instantaneous axis, about this point over here. Let's now check actually if I would get the same angular acceleration if I considered if it agrees. If that angular acceleration is consistent with that frictional torque. And I will actually already start from the fact that I found the frictional force. So if I think about the center axis passing through the center of mass, what will be the net torque? Gravitational torque would be about the center of mass. 0, because center of mass overlaps with center of gravity. Normal torque would be 0. So the only non-zero torque is frictional torque, right? Well, here I found the value of the force, right? So frictional torque, and I'm going also to consider the component in. Right, so I have to multiply frictional force by radius. This will give me the component of the torque, which means that torque is 1/3 radius of the disk mg sine theta. Now, what should be then angular acceleration of the disk? I have to multiply it by moment, appropriate moment of inertia, and I should get that this is the net torque. What should be moment of inertia? Correct, 1/2 mr squared, because it is only it's moment of inertia about an axis passing through the center of mass. All right, so from that I will find that angular acceleration is m and m cancels. Now I have to multiply both sides by 2. So I will have 2/3. Now here I have r squared and here I have r. So I will end up with r in the denominator, and here I will have g sine theta. So this would be the acceleration, angular acceleration, if I use the torque, the frictional torque, and consider Newton's second law about the axis passing through the center of mass. And in what state actually does this result put you? Shout. We are happy, right? How do you see that you are happy? Why we are happy? It's the same value as if I used if I analyze everything about the instantaneous axis. All right, now how about what will be the speed of this object after t seconds? Let's say that I release it from rest, and how to find its speed after t seconds. How about actually if we come back to this problem tomorrow and try to find out speed using both Newton's second law and these results, and work energy theorem. All right, thank you very much, and see you tomorrow.